This is the formula for approximating a function with a Taylor series. But where does it come from? My goal with this video is to take you on a three-step journey to hopefully show you that following a mathematical line of reasoning, you too could have discovered the Taylor series for yourselves. You might be wondering, similar videos on this topic exist. What value does this video add? Most intuitive lines of reasoning jump straight into how a function can be approximated by an infinite polynomial and why we use the derivatives to find the coefficients, saying that it makes the polynomial match the slope, concavity, etc. with the original function. It has always left me with the question of how we arrived at using an infinite polynomial approximation and using repeated differentiation to find coefficients. And while these are brilliant ideas in themselves, they feel like two big leaps in reasoning to me. In this video, I hope to show you that you could have come up with these ideas yourself. With that out of the way, let's get right to it. So let's say we want to approximate the function e to the x. What is the easiest approximation to make? A constant. We'll just sample our function at one point, say x equals 0, and that'll be the approximation. Okay. Admittedly, this isn't very good. It's only correct at one point and it diverges quite quickly. Is there any way we can do better? Perhaps an approximation that is correct at 2 points? Well, it's not much better, but it's a start. Let's sample another point, say x equals 1. Now, if we couldn't see the real function given 2 points, what would be our best guess as to what this function could look like? If you said a line, you'd be correct. Let's generalize this approximation to any 2 points, x1, y1 and x2, y2, and we'll start using the general 2-point form of the line. Let's play with this 2-point form a little bit to see if we can somehow make it easier to work with. Let's start by substituting f of x for y in the 2-point form. Now, it'd be nice if we had some way to reason about how good our approximation is depending on our choice of x1 and x2. But thinking about changing two values at the same time is kind of complicated, and it would be nice if we could somehow get rid of x2. What if we rewrote it in terms of x1? Let's say x2 equals x1 plus h, where h is some distance. We are still thinking in terms of two values, it's just x1 and h now. Hey! After all is said and done, the expression for the slope of this line looks suspiciously like the definition of the derivative taken at the point x1. The only thing missing is the limit. So let's take the limit. Now, this may feel a little arbitrary, but recognizing patterns and exploring things that look similar is a big part of inventing new maths. And look, we've arrived at a linear approximation which only uses one point, x1. If we plug in 0 for x1, we can now go back to the original graph and see what it looks like. It shouldn't be too surprising that the line is a tangent, since by taking the limit earlier, we brought x2 infinitely close to x1 in some sense. The question now is, how could we further improve this approximation? How about if we increase the number of points that we sampled? Let's try 3. Once again, if we couldn't see the function and only these 3 points, what could be our best guess as to what the real function might look like? If you said a parabola, you'd be correct. This approximation seems to already be doing much better. Let's play around with it and attempt to generalize it as well. We'll follow a similar line of algebraic manipulation as before, rewriting all the y's in terms of f of x. Next, we'll rewrite x2 and x3 in terms of x1. I'll also substitute x minus x1 for x in the equation of the parabola. This only affects the values of a0, a1 and a2, as our choice of x1 is arbitrary anyway, so there is no loss of generality, but this form will make solving for the coefficients much easier. Now, plugging in x1 into the equation will give us the value of a2. We have to do a little more work for getting the values of a0 and a1. Plugging in x1 plus h gives us this equation, and in a similar manner, plugging in x1 minus h gives us this second equation. We can solve these for a0 and a1 by adding and subtracting the equations respectively, and you get the following values. Notice that once again the expression for a0 looks suspiciously similar to that of the second derivative with an extra 2 in the denominator. Also, the expression for a1 is once again suspiciously similar to that of the first derivative. Taking the limits again and making the substitutions for a0, a1 and a2, we arrive at the final approximation. Let's now plug in 0 for x1 and see what the graph looks like. Once again, the parabola is tangential to the original curve, since by taking the limits earlier, we brought x2 and x3 infinitely close to x1. What happens if we keep increasing the number of sampled points further and further? That means the approximation is exactly equal to our function at more points. Hang on, what if we sampled an infinite number of points? Would that make the function somehow exactly equal? Okay, but there's a few problems with that idea. We can't exactly visualize an infinite degree curve on a graph, and how do we even solve for an infinite number of coefficients? Let's go back to the abstract for a bit and see what we have so far. To get both of these approximations, we started with the general forms of the curves of degree 1 and 2. In general, the curve of degree n looks like this. So following our idea of approximating by sampling an infinite number of points, if we just turn that n into infinity, maybe we have a start. Okay, but how do we solve for an infinite number of coefficients? It feels like the coefficients should somehow involve higher order derivatives following the pattern for 2 and 3 points. And this is the final insight. Notice that if we differentiate the polynomial n times, it eliminates the first n terms and we can pull the first term out of the summation, and it doesn't involve x at all. So if we plug in x1 for x, every single remaining term goes to 0, and we get an expression for an. And just like that, we rediscovered the Taylor series.